Good afternoon. I hope you're all relaxed, and I want to make you quite enjoyable time for the next hour, so don't stress yourself too much. The thing, when I heard the title of the conference, I asked myself, do they really want to talk about climate change? Very strange in architecture. Normally they talk about aesthetics, or normally they talk about changing of methods, but do they really? No, then I understood that in the end I misunderstood the title. But nevertheless, first of all, I want to say that I'm very pleased, and I want to say thank you for this very nice invitation. It's my second time. I had the opportunity to visit Pamplona, and you know that Austria and Spain had a long history together, and so when I come to Spain, I always feel a little bit at home, because in Austria to be at home always means the same thing. It's a part of the history. It's already long ago, but nevertheless, I then considered myself, what should I talk about? And so I want to adapt this title first. Not in the second part of the lecture, I will talk about climate change and the impact of architecture into relation of climate change as the state-of-the-art knowledge represented by the researchers who deal with climate change. And in the first part, I interpreted the title in a little bit differently, because I believe we live in a society which changes more dramatic than the society ever changed in history. Maybe in economic terms, the changing from the 90s to the 20th century was the changing from an agricultural-orientated society to an industrial-orientated society. But at this moment, we live in a period where we live in a changing from industrial-orientated society to a service-orientated society. But what does this mean in relation to architecture or in relation to society? So, the only thing it really means that the future must be different than the past, because there is no other discipline mirroring the values of a society so much than architecture. Because architecture is not an individual task, it's always a task where a lot of people of the society are involved. So architecture never represents only individual thinkings and feelings, but always the social developments represented by the government, by the local authorities, by the investors. So architecture is always something very complex. So what is really changing? So first of all, I want to compare very shortly. In 1900, I want to, only in two big numbers, I want to compare the beginning of the 20th century to the beginning of the 21st century. What are the real big changes which happened? The first, the average lifetime in a city like, I only can give you numbers. When you want to hear precise numbers, I have to give you the numbers of Switzerland and Austria, but more or less a lot of these phenomena are very well reasonable in a lot of other countries. The average lifetime in Zurich was in 1910, 38 years. Nowadays, it's 84 years. So we are in a completely new situation where we never had in history a comparable demographic constitution of our society. And you think at the first glimpse it's not that important, it has not that much to do with architecture, but when you talk to people from medicine, then and you ask them why the development of this lifespan expectancy It's always very simple, because the living conditions in everyday life of normal people increased so much. So the biggest contribution any discipline did for the development of the lifespan was architecture. Even when architects don't see this that reasonable, but it is the way it was. There is a second number I want to, and you can imagine when we would go on for another 100 years like this, the young people under us, they would end up at the age of 190, but also the doctors say this will not be possible, because there are two limited elements in your body. It's the brain and the heart. The brain and the heart are the only cells in your body who don't renew themselves. So they are really as old as you are. Very strange. But nevertheless, this is the limit, you know. But I give you an architectural number, which is also very funny. In 1910, in a city like Zurich, which was quite a rich city even then, there was 18 square meters of built environment above ground per capita. Nowadays, it's about 90. I don't know the exact numbers in Spain, but they are very similar. When we would go on doing the same thing for another 100 years, we would end up with a number of 470 per capita, built over ground area. This is not reasonable. There is no chance that this will happen. So at a certain moment, we really live in a period, I could give you now a lot of other examples of this kind of thinkings, but we have to understand that our times are changing times, more dramatic changing times than anything else. So I believe at a certain moment we have to do, in a theoretical way, two things. On one side, we have to ask ourselves, what out of the knowledge of the 20th century is reasonable to be developed further on for managing the problems of the 21st century? And the second issue is what kind of new questions will raise in the 21st century which we did not raise in the 20th century. So when I think about the future, and when we have the goal to create long-lasting developments in architecture, in urbanism, or in settlements, I think there will be three key questions which are not properly answered until now. Sure, we know that the goal of this development is, in the end, the individual well-being of the people, the social stability of our society, and to control the environments in which we live in at the moment. And I think architecture has to answer three questions in the future, which were not that clear on the table until now. One question will be, what is the right density for the development of the future? Why do I ask about the right density? Because the density is always related to the mobility question, to the way how we manage transport. And all the historical development of cities is all related to this question of how did we manage transport. And I think we already know two things which are very clear. On one thing, the most important way of mobility of future will be walking. Even when you talk to I had the chance to talk to the board of Mercedes, and they know their company will not exist in the way like they are in 20 years, because mobility will change so dramatically. So for them, it's a big task. How should they develop? But for us architects or for urbanism, it's a big task. what kind of density will these new settlements be related to? And when you, especially also in Spain, when you look on a lot of settlements, but also in Germany, in Switzerland, and everywhere, but also in Spain, when you have a look on a lot of settlements which were built in the last 50 years, are they really able to manage the future? In a lot of cases, we will have to say, no, they are not able to do. So the second question, which I think is also very important, when we speak about the use of the building, which is the theoretical backbone of the architectural theory of the 20th century, it's the program, the use of the building. When you do research about this question, then you know every 20 years the use of the building is changed. But our buildings are not prepared for these changes. And at this moment, we discovered to tear down a lot of buildings, for example, in Switzerland or in Germany or in Austria, which are not even 40 years old. Why do we tear them down? Not because we are too rich, not because this is ecologically useful. No, it's the other way around. It's economically a disaster, it's ecologically a disaster. But we tear them down because nobody likes them anymore. They are not capable to implement the demands of the society of our times. You know, and that's a big question also for Spain, because you have a lot of developments which are not that well occupied at the moment. And sure, there are economic reasons, and we can wait now for a long time until economy comes back to a level which we were used to. But on the other hand, we also have to say that a lot of these developments are not very well accepted in social and cultural terms. People don't like it too much. So that's a big question. But I only speak about, when I speak about openness of building, I speak about one of the big questions which is not answered in theoretical terms in architecture. How can we generate a building which is open to be adapted by history to different kinds of uses? Normally, I always ask my students or other people, do you really want to live like your parents? I never heard somebody who said yes. And I asked the people who are working now, do you really want to work like you have been working 25 years ago? I never heard a lot of people who said yes. They always want to have some social and development, and you know, especially the buildings, you know, which are very much determined to the idea of family, which is a central idea of modernism. They have a big problem. Why? Because in our societies, people marry much later, but therefore they get divorced much earlier. You can see this in statistics very clear, and in cities like Stockholm or Zurich or Hamburg or Frankfurt, 90% of all households are already one or two person households, which cannot be a family. So there's a big problem that during the period when these things were developed, we were believing that the situation, the social development will stay stable. But in reality, it's not. I can tell you the most funny country in this development, it's Iceland. Maybe you know in Iceland, 92% of all the children are born outside the family. So that's a big issue. I can also give you numbers from Sweden or from northern countries. I only want to say that when we speak about buildings, we speak about a very different time frame than when we speak about the use of the buildings, because the demand to the use will be changed. And I think the third one is very clear, the resource efficiency. Everybody knows when all the other parts of the world would live that stupid than we live, we already need 2 planets. So Europe is really a really bad example for all the others. I'm really sorry. that we spend and waste too much of materials. And when we speak about resource efficiency, we do not only speak about energy or water, but we also speak about sand, about copper, about steel, about a lot of materials where at this moment in global terms, we really have a problem to how to integrate them or how to make it possible that all the other people in the world live as stupid as we do. Very strange. At this moment, we are still very lucky because they don't do. They cannot afford. But we should be very strange, you know. It's very frightening when we imagine that they can afford the same things than we can. So at the moment, we live in a very strange, balance of different situations. No, but nevertheless, you know, out of these thinkings, I don't want to go into this in detail. I don't want to go. Out of this, we developed a kind of understanding about when we want to speak about sustainability, or then we have to speak about time frames. You know, because you all remember this very nice book of Gideon about time, space, and architecture. We were talking a lot about space during the last 50 years, about architecture, but we did not really talk too much about time. But when we deal with this question of time, then we have to understand that a building nowadays is an overlapping of 5 different, very different technical systems. And these technical systems, in a long-term view, they have very different lifespans. And that's a little bit a contribution to this resource efficiency, which I will explain you afterwards. So the first question, which will last longest, which is the most important decision about architecture in the 21st century, it's very simple. It's the question of the contribution to the public. So the key question for architecture in the 20th century was a little bit, how good does the building work? How good is the use of the building? How good is the function of the building? At the end of the 20th century, we learned to understand that the feeling in the building is very good, but in future we will have to learn what is the contribution of the building to the public. So I say always like this, the most important user in the 20th century was the person who moved into the building. But the most important user of the building in the 21st century will only be the person who passes by. Because in the feeling of in the emotion and in these values of these people, of the person who passes by, there is the future of the building. Because we don't need a first user, we need a second user, we need a third user, and this is a question of the value of the building, how it is accepted in a practice. Now, I tell you something about Switzerland. You know, Switzerland is the only country in the world which in its constitution it is written that the sustainable development is a goal of the Swiss constitution. But when Swiss people speak about sustainability, it's something very easy. It's something, how can we keep up the values of our society in economic, in ecological, and in social terms? So everything is related to a question of the time frame. And therefore, there is a law in Switzerland, when you do a structure of a building as an engineer, you have to guarantee for 100 years. And if there is a damage in the building earlier or before, the structure is understood as the load-bearing quality of the building and the vertical organization of the building. And if there is a mistake, don't be the son of a Swiss engineer. It's dangerous. don't be the son of a Swiss engineer, you know. But it's by law for more than 100 years, and I think it's very reasonable. But when you understand that this part of the building should last for more than 100 years, you can imagine that they think about and I believe also, that the value of the building should generate benefits to the society in a much longer term. And that's the relation of the 200 to 100. The next one is also very simple. When we do research, we always find out that one of the most long-lasting parts of the building is the envelope of the building according to economic terms. And the envelope becomes more and more expensive in a building, even in future. So the average lifetime at the moment in the existing building stock is about 50 years. And then the function, the program, the use of the building is only in average time 20 years. And the more specialist, the more specific the function is, the shorter the lifetime. Maybe you know all hospitals. Hospitals are the buildings which are, the building cost for hospital is the running cost. Because you change these buildings and you have to adapt these buildings anyway. You know, so be very careful when you do very high specific buildings. And the next one is the surface, you know. The surface including all the technologies, all the heating, cooling, ventilation systems. And at this moment, everybody tells me we save the world and we save the climate change by doing investments which have a lifetime of 10 years. I'm sorry, the 10 years I didn't invent, you know, that's how these industries are living on, you know. So I don't believe that we really can adapt the climate change or tackle the greenhouse emissions by using a lot of technology, heating, cooling, mechanical ventilation, and these systems, which in average have a lifetime of less than 10 years. Very strange. I don't know why we believe this. I'm sorry, I don't believe this. So the question is now, I want to show you a little bit. So that's the contribution. Now, yesterday I heard, I was not here. You see here the contribution of the greenhouse gas emissions on the planet at the moment. The buildings, it's the maintenance of the buildings, it's 18.4%. The agriculture is 27%. The industry overall is 20%, and 13% is about what we call in future the gray energy. The gray energy is all the energy which is used to produce all the materials what we need in the buildings. Otherwise, and you see the transport at the moment is very low, only 14.3. So electrical cars are nice, but they will not change the greenhouse gas emissions. I'm really sorry, it's very low. But when you calculate together, to 18.4 plus 13, so that's the global number, is about 32% at the moment is only related to the questions of doing and maintaining buildings. This number, that's a global number. The number is, it's a summary, it's from the International Climate Council, which is a United Nations organization. These are the numbers of 2010. They adapt them every 2 years when they have their conferences. It's not that different, so I still have it there. So architecture is the biggest contribution to greenhouse pollution all over. I'm really sorry. And how different this can be in different countries. I give you a number of Hong Kong. Hong Kong, 91% of all the greenhouse pollution of Hong Kong is only related to the buildings and maintaining buildings. Because in Hong Kong, dehumidification and cooling is so important. So this can be very different. In a country like Switzerland, this number of the building is not about 34, it's about 55%. So the problem is that the developed countries, they contribute so much through their building stock to this question. So that's a very, you can, look, when you see statistics like this from the Climate Council, you should always know that this means 80% of the researchers engaged in this council believe that this is true. It's not 100%, it's 80%. So you can say, okay, 80% are too stupid, that's fine. I believe maybe there are 2 who believe something very different, that's also fine. But as a starting point, maybe it's nice to talk about the thinking of 80%, So only, I don't say 100%, but 80% of the researchers involved in this question believe this is right. So I know that you were talking yesterday about the cows, the green things up there. It's also nice, but when this would happen in Switzerland, I would say it's a Swiss behavior, because normally when in Switzerland you tell somebody you failed, he always tells you, yes, but the other one also failed. But this is a funny story. I don't like it that much. It doesn't mean anything, so I'm sorry about this. Okay, go to the next one. So there's a second issue, which, and now I come to 22, 26. There's a second issue which is quite important. This is an Austrian statistics, when the blue line is the growth of the average income. The red line is the growth of housing costs or real estate. And we have this phenomenon at the moment all over the world, that the incomes and the real estate costs, they develop very differently. And behind this, when this goes on like this, you will see a lot of social tensions. You will see a lot of social questions, and you will see a lot of social fightings. And this is very funny that this is a parallel development which I can see nearly in every country. So when we were talking about 22, 26, I'm mainly talking about 2 questions. The one is how to make buildings more efficient in maintenance and in investment cost for the user. Second question is how to increase the comfort, or at least keep the same level of comfort by reducing the impact on greenhouse gases, on carbon dioxide. So, look, we are working on this now for more or less, look, when I was young, the first political remembering I have in my mind was the oil shock 1972. I was a student then, and then the highways were empty. And I thought, this cannot be the future of our societies, depending on these things. Nowadays, we discuss this problem very differently, because we discuss about greenhouse emissions, but nevertheless, it's the aim, it's the same background, that our society is very much related to carbohydrate production. And we are working on this now for more than 30 years, and you see these are 2 buildings, and you see there is a time difference of 8 years. The Munich Re, already then, as you saw also in the presentation of Louisa Hutton before, is a company who is very ambitious in reducing their impact on ecological development, and the university, the ETH building is, that's only, these 2 numbers is only a difference of the knowledge of 10 years. That's the progress which is at this moment in a lot of materials, in electrical efficiency and things like this. But what you see already in both scales, that the space heating, cooling, and ventilation is becoming a smaller and smaller percentage. And that's what we learned very hard during the last 30 years. The more you focus on these things, the more you increase the knowledge, the percentage and the impact of heating, cooling, and ventilation becomes smaller and smaller. And now this is only 3 buildings I will show you. This is ETH. It's a university building at a campus in Zurich. And this building is used from many different departments. And it's the best performing building in social acceptance and in energy performance of the whole campus. You know, so for us it is always very difficult when we speak about energy as an abstract numbers. In the end, it's a question of comfort, acceptance, social and cultural acceptance, and performance. And so this, for example, you will have a look on this building. So one of the very simple thinkings about this building is that there should be no sun on one piece of glass from the 28th of April until the end of October. So all the geometry of the facade outside is only a geometry of shading. And now there is a very small advantage of these shading systems. You know, that's very funny, but researchers, which are mainly working in this building, still a lot of researchers are smokers. And normally smokers have to leave the building when they want to smoke. But for a lot of researchers, smoking is part. So I made a building where even the smallest building, has a direct access to a balcony. And so because all the glass windows over here are sliding doors, and every researcher can go out of his room to his balcony to have a cigarette. And this is the most communicating zone of all the building, you know, because people meet outside there, they talk, and they like this access to have to the fresh air. In a normal, high-developed university building, you have closed windows. But they appreciate very much. So we invented or developed together with the engineers a system where when somebody opens his sliding door, all the mechanical support of the energy system in this area stops. And only when he closes his door again, then the machine, so it's really high-tech, you know, it's not. So there are a lot of sensors in every window that when you open, energy support stopped. When you close, energy support on again. But this is something very funny that in this building, that's what I found out, there are people who nearly 300 days a year, they open their window. It's more comfortable for them. It's more comfortable. Okay, now let's go through the building very shortly. And then the second is what we also, you know, all the interior part of the building is about natural daylight. And then this is this is a lecture hall. This is the only main lecture hall in the building, but when you have a look to the green and right walls, you see you can move all these walls. Because the main use of this area is not a lecture hall, it's the launch for the students. So that's the area where students have their meetings. And as you know, in a research building, lecture halls are used less and less. And all the colors in this building are done by a Swiss artist called Adrian Schiess, which I like very much. And I only invited him to do this. You know, this is the outside of this building. Now you see, when you see the trees, that it's quite old now. And now I come to 22, 26 first. Look, how is the relation? I gave you very short numbers before about these complexes. You know, in the end, I only will, when we speak about buildings in future, we speak about comfort. And you know, comfort in physical terms is mainly, it's about acoustics, it's about humidity, it's about air quality, and it's about temperature. I'm very sorry, according to time, I will only talk about the issue of air temperature at the moment. And you know, there is a lot of knowledge all over the world that people feel well, more or less, between 22 and 26 degrees. So when you hear the name of the building, it's very easy. Never under 22, never over 26 degrees. You know? And in the end, you see the blue line is representing the development of the outside temperature during 1 year. So this is very important that you understand. When you speak about building physics, you always have to think about not one situation, but 1 year. And then you see there's a green line according to the use of the building. You know, there's an inside temperature which is not parallel to the outside temperature. And then there is a gray zone up here where you seem to feel well. That's the 22, 26. And then when you're an engineer, this is a very nice diagram because on the red areas, you know you have to heat. That's the capacity of heating. On the blue level, that's to cool, that's the capacity of cooling. But when I'm never interested in the red and the blue, I'm always interested in these very short periods, you see here, where you don't have to do anything and everything is fine. So what we developed during the last 20, 30 years is a strategy which we called to optimize the building. And to optimize the building, and then you get results like this, that the period where you don't have to do anything becomes much longer, and as a natural result, the overall amount of heating and cooling reduces very much. So in the end, you will ask me now, how do you do this? But in the end, this optimization is only about architectural, geometrical questions. So in every situation in the world, according to the local climate, and I pronounce the word local because every city is quite different according to temperature, therefore you need a lot of data. You can optimize a building in relation to architectural questions. And the result out of these questions, you can now find which is the most reasonable building for the exact situation in which you build. And now I show you very shortly the 22, 26. This is a very small building. It's 3,000 square meters. It's about 500 square meters every floor. And you see there are thick walls, but they have nothing to do with the heat capacity of the building. It's only something I like a lot. I like thick walls much better than small walls, so I normally like to make thick walls. This is more with structural problems than with U-value heat. And then you see the only thing I'm not interested in the building, there is no program in the building, because all the different rooms will be occupied in a very different way, and history will show. I will lead you now very shortly, now in theoretical terms, what we did in the building. Look, now when we develop a building nowadays, I'm always interested in some very simple question. How will the building behave in temperature developments without that anybody will ever go into the building? I want to know the green line. You see the green line? The blue line is the outside temperature, and you see the blue line is the outside temperature of Zurich. And you see the green line. What is the materialistic condition of the building, and how will the building perform in relation to the outside temperature over 1 year? And that's a question which is very difficult to answer in physical terms, but that's the main issue what I'm interested in. The second thing is, now when you see the green line again, then through the use of the building, temperature level will raise as a starting point. And now at the third step, what we do with software, why we determine the behavior of the building by software, that's this area you will reach 22, 26. So it's 3 steps. First, the materialistic question of the quality of the building. Second, which are the scenarios of using the building? And third, what can the software do in relation to the building to adapt, to optimize this kind of temperature? Now, there is another issue which is also very important. You know, the red line is the potential of use of sunlight in the building. The blue lines are the areas where you need artificial lighting. And so it is very important that you do a building which does not need artificial lighting all through the year, only according to winter time or summertime or things like this. This is the building now. It's 6 stories high. And you know, what can the building, look, okay, now when you, when you calculate very properly a modern building using a good glass, using quite reasonable materials, making reasonable percentages of openings and things like this, you will find out that only 20% of the energy demand of the building is related to the outside temperature. But 80% of the energy demand is related to the people to the use of the building. But when you go into a building, what kind of impact do you have to the building? First of all, you bring a lot of temperature with you. I don't know if you know, but you are quite bad heaters, but everybody of you brings with him about 80 watt per hour. So when maybe there are some bolded people here, okay, doesn't matter, they bring in, oh yes, he will bring in about 110. You know, it's a very physical, very simple idea, surface, temperature, very simple. So you bring in a lot of temperature. Second issue is also very simple. During one day, you lose about 1.5 liters of water. So the humidity, you bring in a lot of humidity. Third issue, also very clear, and that's the key issue, you do the opposite of trees. You take oxygen from the room and you give carbon dioxide back to the room. The trees do exactly the opposite, you know. So now, to these simple phenomena of air quality, 80% of the energy demand is responded. So we asked ourselves, what happens if you, therefore we asked before, what happens if you don't do any, if no people are there? Temperature will behave like this, that's fine, but nothing else is necessary. Only when people go into the building, then you need these very different levels of comfort. So we calculated that we said we don't want to have a building which is not generating some conditions which you can use or not. We wanted to generate a building which reacts on the impacts through the use of the building by the people. So now in physical terms, I'm sorry about physics, but that's okay. It's a very complicated issue. The question is, how many cubic meters of fresh air do you need in 1 hour? And how is the relation of the cubic meter of fresh air in relation to the temperature, to the 80 watt you bring with you? And I can tell you now very shortly that, more or less the secret is this. You bring as much energy with you that all the air which you need for having a good air quality has at the level of 1 degree plus. And So until 1 degree plus, when you can guarantee that you don't need more energy, that you don't need more fresh air than which is needed for your health or for your well-being, everything is fine. So a lot of ventilation is very strange. Maybe you remember, some of you went to churches when they were young. And in a lot of churches, when there is a nice balance between the height of the room and the people in there, air was quite reasonable, quite well. And so this is a little bit the same phenomena, but only a little bit calculated more. So we wanted to have a building which reacts on the traces which are done by the user of the building. So in the building, in every room, there are sensors about temperature, about carbon dioxide, about humidity. And in the end, the software calculates what the building should do. What can the building do? The building can only do two things, very simple. It can open himself and close himself. And secondly, it can switch on the light and switch off the light. The light in our climate is only good for heating, because the heating becomes so small that it's not very interesting. So it's only about opening and closing. Now, when I would have much more time, I could tell you much more about physics, about heat capacity and things like this, because there's a lot of phenomena which are not integrated properly in the software which we are using now to determine our buildings. You look, in my lifetime, I had a very big advantage that I never was talking to the people who use software. I always have been involved in talking to the people who develop software. And the guys who develop software, they know exactly where their mistakes are. But the guys who use the software, they know never, because they believe the software. It's a big problem. But because they never have the chance to ask the guys who develop the software what's going on. And that's a real dramatic development, what we have at the moment, that we believe the wrong things because we don't understand them anymore properly. But nevertheless, that's okay. Now we go, you see, I can show you now a lot of diagrams. Every room is measured since 3 years, 24 hours, every 10 seconds. You know, so we have so many, I think there's no building in the world where you have so many measurements for every place, every room, all the time, every 10 seconds. You know, we can print you books like this as long as you want. It's not a big issue. Now I show you different rooms. The red lines is always the carbon dioxide, the blue line is the outside temperature, the green line is the inside temperature. Then you see, you can imagine that out of this, when you don't have to move anything anymore, the maintenance costs shrink rapidly. But I don't want to talk about this. Okay, that's the building. It's done in very traditional materials from local backgrounds. So all the buildings technology is very simple. Everything which is horizontal is in concrete. Everything which is vertical is in bricks and plaster. That's it. Nothing special. Nothing special. There's a lot of art on the ground floor we have an art gallery. Then next to the art gallery there's a restaurant, and then an upper place on upper stairs there are two offices, and about half of the building is rented out to different companies. So the first floor is public. Second and third floor we use ourselves for our own company, and the upper 3 floors are rented to different companies. And they also, you know, they after 3 years they also believe that they don't need any additional things. Okay, Now, look, in the end, this is what my area is famous for. It's massive wood production, massive wood furniture. So all the good architects of the world, when they want to have massive wood furniture, they go to this area. And the nice thing about this massive wood is that you have no glue, you have no screws, you have no nails. It's only about knowledge how to put the things together. And sometimes these massive wood tables I like very much because they are something of what I believe in architecture should be in a long-term view. That we have to knowledge how to put the things together. Very simple things, one material only. The secret is only the knowledge how to bring them together. Now that's the third project I show you. This is a university in, as you remember maybe the image, this is the University of Luxembourg. It's just opened a few months ago. It's about 50,000 square meters big, and this is the first high-rise building in Europe having no mechanical ventilation, no cooling anymore. It's not that radical that there is not heating anymore. It's only a small heating left over there, and that's the entrance of the building. That's the site in which the building is built. It's a former iron production place, and then you see, and therefore in all the building we used very much this atmosphere of this industrial area. So we used the rough materials from steel and concrete, and relating to this site. And you see these are different images out of it. And then you see once more, and out of the windows into this old industrial area. And this is the first building. This is the last building. Sorry, it was 4 buildings. This is the last building I ever want to show you. And I only want to show you this building because we know that this is possible to do a building only by knowledge control for a long time. And this is the first building I dared to build without any technology. So no heating, no cooling, no mechanical ventilation. The building is quite old. I built it at the beginning of the 2000, something like this. And why did I dare to do this? Because the client of this building is a woman which owns a small harbor at the lake of Constance, at the Bodensee. And at the end of the year, she always comes up to me and says, "Oh, I earned a little bit of money. Can we build something?" So every year, we do a small project together. And I asked her why, and then I asked her, "Why do you do this?" Because I learned that good architecture can increase the quality of my life. Thank you very much.